The demonstration is devoted to one of the options for building a failover cluster based on CBSD for containers and virtual machines. Recall that building clusters based on FreeBSD is the main and ultimate goal of the CBSD project. We will also give a detailed explanation of why CBSD introduced the concept of independent working directories within a single host. The initial state of demo cluster is two nodes named CARP1 and CARP2, each of which initially owns a separate CARP address. Looking ahead, let's say that the address in this cluster is not tied to a node, but to a pool. Therefore, this is called the pool-binded cluster architecture. Also in the reference installation, each server is responsible for one pool, Pool 1 and Pool 2 respectively. Some CBSD users naturally ask how they can mount a resource, be it a virtual disk or directory, located on another pool for a virtual machine or container. These questions are a good example of how the CBSD clustering concept can be broken, and since most CBSD users only use the tool locally on one node. This demo will show the project in a completely different way. In addition, we will show the user different ways to interact with CBSD. Ready? Let's go. The concept of independent directories in CBSD is similar to Python's virtual env. All resources related to containers and virtual machines are in a unique directory. The need to have a complete copy of base dir or ISO images, even if they are duplicated, is due to the need for live migration of virtual environments. For example, if we call CBSD-JLS on any node, we'll get a message that the working directory has not been initialized. There is no default working directory. However, we can specify the path to the directory, which is the working directory through the environment variable, and we can create isolated resources. You can see that on the first host we created a container via jconstruct2e in pool 1's working directory, and on the second host we created a container in pool 2 via cbsd-jcreate. In other words, CBSD may not work globally, but can subscribe through a broker to events intended for a particular pool. Also, CBSD has a Grafana dashboard to display the status of containers. For clarity, we divided it into two parts, for Pool 1 and Pool 2. Pay attention. Here we monitor not a host, but a pool. That is, the resources are not tied to a physical host, but to a pool that can be located on any server. This is about working directories. Now back to the main topic of the demo. Let's start by demonstrating how you can work with a CBSD cluster from other operating systems. We use an operating system running Windows 10. On which we have a thin client for a CBSD cluster called NuBect-L. Ready-made thin client builds are available for all modern operating systems, for BSD, for Linux, for Windows and macOS. To work with a thin client, we need to specify two parameters, the path to your public key and the URL for the CBSD API. An important detail: behind the API there can be any number of physical hosts with CBSD, which can host any number of pools. In turn, pools can consist of any number of disks. That is, it is a completely scalable both vertically and horizontally cluster platform. In our example, we use only 2 servers and 2 disks configured crosswise. This configuration avoids the use of systems such as DRDB, HASTD, Ceph, Gluster, etc. We replicate data at the ZFS transaction level and get integrity thanks to ACID principles. Even if some kind of disaster occurs and the file system becomes inconsistent, we can roll back to the last working transaction. This guarantees the safety of the data. With a cluster of this type, the nodes must be located in the same data center and have a good communication channel. It is highly desirable to use network interface aggregation via lag. If you are interested in building a multi-data center cluster based on CBSD, you can read the article on CBSD VPC based on VXLAN technology. So, we create a FreeBSD container from Windows OS. Unfortunately, Windows does not have an SSH client in the base system, but fortunately, the thin client has built-in SSH support and we can log in from the Windows operating system directly to the FreeBSD container via NUBECT-L. We are seeing some garbage related to ANSII codes upon login. This will need to be fixed in the thin client in the next release. For the sake of experimentation, let's create a few more containers to see how they will be created and distributed across the cluster. If we had one server, it is quite obvious that virtual environments were created on only one host. But in our case, we get a 50-50 distribution, in round-robin mode. This is how the default DRS, Distributed Resource Scheduler, recommendation works if the hosts are exactly the same. The CBSD API calls an external script as a recommendation. So you can describe any of your logic in your favorite programming language. For example, depending on what flavor the container and virtual machine are requested, for example, with a large number of cores or requiring a large amount of RAM, or you need a fast disk or you need a large disk, then your politicians can take this into account and choose the most suitable server for VM or jail configuration. Since we collect all the node metrics, we have all the necessary information for issuing flexible recommendations based on different policies. But in this example, we have the same nodes and create the same containers, so we get round-robin. In this demo, due to an error in the script, ract-stats, which exports data, was not run, so we will run it manually. So, we managed to create a container through a thin client, and now we will show how to create virtual environments for a CBSD cluster without having a thin client or a mobile application. We'll show you how to create resources in the raw so that you can understand the simplicity of the API. Also, it gives you the opportunity to create your own UI of any complexity to your taste. We use a small JSON file. This is not the entire payload, only the minimum number of parameters is listed here. Note: we already have a container named test1, since we created it from Windows OS. In the terminal, we will use a different public key. And so we can create another container with the same name. In other words, we don't need to know that someone created virtual resources with the same name. We don't care about it. They don't overlap because the names you choose are mapped into internal CBSD name sequences. From the point of view of the cluster, this is a completely different container. To simplify, your public key is your namespace. For example, let's remove the test1 container from Windows OS through the thin client. We will make sure nothing happens to the test1 container created from the console. Also, we can display summary information on our namespace. Of course, it will not take into account other people's resources. We see here only our own virtual environments created within the quota allocated to you. Recall that the namespace is a derivative of your public key. Therefore, by default, this method is only applicable for trusted environments. For unfamiliar users, a token based on other algorithms should be used. Finally, the third, rather interesting method for creating containers and virtual machines is the CBSD file. By default, CBSD file works with a local CBSD installation. But if you add the cloud_URL and cloud_key variables, you start working with a remote API cluster. CBSD file is well suited for some kind of bulk operations. When you can create any number of environments in one command. For example, now we are creating a container named boo. If the status is given, it means that the container is already ready to work. Tellingly, when you are in the CBSD file directory, you are limited to only those environments listed in the CBSD file. For example, if we try to login into the container named test1 that we created earlier, we will get a message that the container does not exist because it is not in the CBSD file. You can operate on the containers described in the CBSD file. If you want to work with containers outside of the CBSD file, just change the directory to something else where the CBSD file is missing. Now let's move on to the issue of container migration. Unfortunately, unlike BIVE virtual machines, this case is not so interesting. Because the containers will be migrated with a restart, it's soft, but cold migration. That is, they will be restarted during the pool migration. By the way, in Dragonfly BSD, where CBSD also works, processes can use checkpoint. The state of the process is saved to a file. It is this scheme that will be shown in our live migration of virtual machines. Now we will show the migration of containers. We put two addresses on the ping. One address belongs to a container hosted on pool 2, which is currently running on host carp2. And the second address belongs to the container from the first pool and the first node. We have the rc-d-cbsd pool command which can list the containers and virtual machines on the respective pool. Also, this command accepts stop and start commands. If you do cbsd pool stop, this will cause your host to give up the master role for this pool. If there are containers on the pool, they stop. If there are virtual machines on the pool, they create checkpoints on the file system, after which carp on this host goes into the backup status. This in turn triggers a carp transition in the master state on the neighboring node. At the same time, changing the status of carp from backup to master initiates the import of the pool and the unfreezing of virtual machines from the checkpoint, Thus virtual machines do not reboot but continue to work as before, and the launch of containers. This is called pool-binded. It does not have to be virtual machines or containers, we can place regular RC/D scripts there to start services. For example, a telemetry service and its configuration, which gives metrics for resources on the same pool. If the pool is imported, the system sees a new service. If the pool is exported, the service disappears. If you do start for a pool, it means take over. For example, now we have performed a soft migration of the first pool. The second node imported the pool from the first node and launched it. There is no copying. There is no data migration. There is no replication. The data on the neighboring machine is already present when the server does start the pool. Thus, two pools are now running on one of our nodes. All containers are alive and well, but already working on a new server. Two-pool is not a limit, but a condition must be met when the server can accept a sufficient number of pools from dead nodes. At the same time, statistics can be interrupted for a short time, holes appear. This is due to the fact that the address can be cached on the switch and therefore connections do not immediately go through. It is logical to attach the statistics service to the CARP address. From a dashboard point of view, there is no change in how the metrics work after the pool has changed ownership. Now let's simulate a server crash. Let's run IOStat so that we can see that the server is active. And in parallel we will take out the power wire for the second server. Quickly enough, the remaining living machine notices that something is wrong. The server noticed something bad. The CARP address of the second pool moved to the master state. Since the turned-off machine stopped being responsible for the CARP state, we see that the pool was automatically imported and we see the launch of containers. At the same time, both pools are in the DEGRATED status, because the pool consists of two disks, one of them is local, and the second is from a remote node. Now we will ping the address of the second node and turn on the power supply of the server. Since the pool is in a DEGRATED state, which is not a good situation, all transactions are now written only to the local disk. When the second server comes back to life, the first server sees this and tries to connect the disks via ISCSI. This is the same as pulling the cable from the disk from the motherboard and then turning it on again. It will look like a short-term failure. After that, the file system must perform some kind of check. In the case of ZFS, the scrub routine will run automatically. By making the stop for pools on a newly launched server, we thereby include it in the cluster as a backup. This does not happen automatically by design. Perhaps the system administrator will want to audit the cause of the crash before returning the node to the cluster. However, the pool will automatically repair itself independently and automatically. The system automatically repairs itself. But out of habit, we also run the scrub operation again manually. Let's now try not to give the pull, but to take it. We do a start on the pull, which causes the master node to give the pull to the new initiator. It will also trigger container shutdowns or virtual machine freezes. Let's carry out the exchange of pulls to the end. Now node 1 serves pull 2 and the environments on it. You have swapped them. Pull moves are convenient when you need to take a node out for maintenance. Thus, we balanced the load and the cluster went into its usual regular state. So, forget about binding virtual machines and containers to a physical machine. This is the most important thing in the CBSD pull-bind cluster concept. If you want to see what a live migration of machines looks like in a similar cluster without a live migration, check out the second part.